Woohoo! Welcome back. Today we're going to be talking about the number e and how we use it in exponential growth and decay. Woohoo! And here to help me is my friend Bacterium. Yay! So the number e has an official definition that involves a term you haven't heard yet, but it is limit, and it means what happens when you let something either get closer to something or get really big or get really small. And in this case, we're going to allow n to get really, really, really big and see what happens. And the expression we're going to use it in has 1 plus 1 over n. So as n gets really big, 1 over n gets really small. So this inside expression gets closer and closer to the number 1. Then on the outside, we raise the whole thing up to that bigger and bigger number. And a lot of people would guess that this would get either really big or maybe flop around a lot or maybe get really small. And what ends up happening, and this is unexpected, but we know it happens, is this number, as n gets really, really big, gets closer and closer to this number, 2.71828, some other stuff. And this is a number that Bernoulli actually came across when he was studying finance and compound interest. And that was in the late 1600s. And by the early 1700s, it had been named lowercase e in honor of Euler. Now, I know his name looks like Euler, but I've been told that it is correctly pronounced, or at least as close as I can get, as something like Euler. So this is Euler's constant. And the first thing we want to do is go ahead and look at a graph to see what the heck this number looks like. So in Desmos, I went ahead and plugged in a few functions. And these functions, there you go, Barry. These functions are f of x is 2 to the x, g of x is 3 to the x, and h of x is e to the x. And so I've got them written down here, and we've got kind of a cool result. E, remember, is about 2.7, so it sits between 2 and 3, and e to the x sits between 2 to the x and 3 to the x, which is pretty cool. E to the x is also closer to 3 to the x, which makes sense because 2.7 is closer to 3. So, woohoo! And then e to the x as a function behaves just like the other exponential functions in that it goes through this one intercept at 0, 1, because when you plug in 0 as an exponent, you get 1. We also have an asymptote at y equals 0, which is just the x-axis. So that's x right here. And that means that as x gets smaller and smaller and smaller, or more and more negative, we've got all three graphs heading in towards the x-axis, but they never quite get there. They get closer and closer and closer and closer and closer forever, which is what makes this an asymptote. It becomes like a fence. So these functions come down this way, and they get kept out of that lower quadrant by this fence, that asymptote at y equals 0. So this is our graph of e to the x, which is pretty cool, and what we expect. So woohoo for exponential growth. Barry is very excited for exponential growth. So then, though, what we want to do in this section is flip some of this around and actually take a look at a problem that involves exponential decay. And so the story is doctors are going to use radioactive iodine as a tracer in diagnosing certain thyroid gland disorders. That's a lot. So basically, radioactive iodine, a form of iodine that is radioactive in a certain way, is used because thyroids, which is a gland in your, it's in your throat, it's in the front of your neck, they love iodine. So if you take some into the body and it's radioactive iodine, the thyroid sucks it all up. And because it's radioactive, doctors are able to sense it and photograph it and see what's happening. So you can take a better look at what's going on inside the thyroid. And this iodine decays And rather than exponential growth now, because this is radioactive, it's actually the substance, the iodine, instead of getting bigger and bigger and bigger and bigger, it's getting smaller and smaller and smaller and smaller. Remember that with radioactivity, what's happening is you get a bunch of stuff together and it's going boobity, 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 boobity. And as all the little bits inside are bunking into each other, some of the bits are going patoo, patoo, patoo. And so it's actually losing little bits of itself, plus it's radiating various waves, and hence radiation. And so the quantity of iodine you have is getting smaller and smaller and smaller and smaller and smaller and smaller, like that. So we can actually measure this, and that's what we're measuring here. We're measuring the mass of what remains after T days as this. And so I went ahead and, using Desmos again, I drew the graph. Pardon me, Barry. There's Barry, very excited. Radioactive decay, rather than starting low and going up high, it starts up high and it heads down low because it's shrinking. Now, since this is the number of days, in fact, this right here is what happens at time equals 0 days. So in fact, this whole graph is not really what we're very interested in. We're not looking at what happened yesterday. We're going to start right here and just look at this part of the graph. And we can see that it is decaying, and in fact, it shrinks really fast. And then as we have less of the material, it shrinks less quickly, if that makes sense. So how much is left depends on how much there was. And as more and more decays, it slows down in its decay. And then it slows down so much so that technically, again, we have that asymptote here. So technically, this curve would never actually get to 0, although in the human body, it would get to the point where we wouldn't be able to sense it, or maybe your body flushes the rest out. So we wouldn't actually be able to measure this off until T goes to infinity, of course, because we just don't have that much time. So Barry's very excited, though, because decay looks like a slide, which is very exciting, too. Whee! Okay, so back to the problem. See how fun math is? Math is so much fun. Okay, so first off, we want to find the mass at time T equals 0. And I kind of gave that away in the graph, but let's pretend I didn't. And let's go ahead and plug in T equals 0 days. So this is kind of a gnarly looking number. It's not that bad. It's just how this particular substance tends to decay, tends to shrink. And I'm just going to plug in T equals 0 there. Now 0 times a negative 0.87 is just going to be 0. And then I'm going to remind you that E is a number. It's a special number. It's an amazing number. It's a number that comes up in all sorts of weird places in math and physics and really is incredible, but it's still just a number. So there's nothing exceptionally magical about how it behaves. If you take E raised to the 0th power, just like any other number other than 0, you're going to get 1. So E is a number, so E to the 0th equals 1. And then you get 6 times 1, which is just 6. So this is our initial mass. And we're told it's measured in grams, so I'm going to write 6g for grams. And that's it. So hopefully, again, some of these word problems look intimidating, but they're going to hopefully start to feel really kind of, they have a lot in common. So once you've done one, the next one is going to look very familiar. And, they're really actually very useful for measuring what's going to happen. So the next question is, how much of the mass remains after 20 days? So I want to know T equals 20. And here I'll do a quick check. What is the mass remaining after T days? Good. You always want to check with word problems like this, especially when they measure time, because sometimes this might be in days, but it might ask you after a week or after 2 months. So double check that your units agree. I've got days and days, so that's good. So M of 20 is 6 times e to the negative, pardon me, Barry, 0.87 times 20. Now this is the exact answer. This is absolutely the exact answer. And I can even multiply 0.87, negative 0.87 times 20 and get 6 times e to the negative 17.4. And this is the exact answer. Sometimes the book or the problem you're working with will expect you just to leave it as the exact answer. My guess is what we really want to do with this problem is come up with a decimal approximation. So I'm going to go a few steps further, but it's possible that the answer they're looking for is this one. But what I'm actually going to do is calculate the whole thing. So let me clear this out. So pardon me, there's my light right there. Let me see, I'm going to move Barry. Pardon me, Barry. You're going to move over here. And then I can put this here, I think, and not run into the light. So I want to multiply this out. And the first thing you want to check for is that you know how to find the e raised to the power function on your calculator. I don't know if you can see, mine is right here. Usually it's near or somewhere above or below the natural log. And we haven't talked about that yet, but if you look for the ln, you'll find the e to the x. Or if you're looking for the ln, you look for the e to the x. So I've got the e to the x function right here, but because it's written in above the key, I'm going to have to use my second. So this is how I'm going to enter it. I'm going to enter it as 6 times, and then I do second natural log, and that gives me my e raised to the power. Notice that it's going to give me a parentheses there. If it doesn't give you a parentheses, you can always type one in. And then I'm going to go ahead and do the opposite. And remember that for the opposite, you want to use this key, not the minus key. It'll confuse the calculator. Sorry, Barry. Barry's having fun up on top of the calculator. Don't worry about him. 0.87 times 20. And then I'm going to close the parentheses, and I'm going to get my value. And this is a very, very tiny amount. A gram is already pretty small, right? A gram is around like a penny in weight, so it's pretty small. And this is, let's see, 1, 2, 3, 4, 5, 6. I get 6 zeros, 1, 6, 7, and some other amounts. Now, the exact answer is going to be 0.00000016, and it may be 166, or we don't know if the calculator has rounded for us or not, so it's close to this. So the best we can do is this, and if I asked you for a decimal approximation, then remember you would do the wiggly equals, and then I would tell you how many digits to go to. For example, if we wanted to go to 1, 2, 3, 4, 5, 6, 7. Let's say we wanted to go to 7 decimal places. I would round to 1, 2, 3, 4, 5, 6. I would round to 2. Oops. Now, when you're doing homework, the number of decimal places will be specified. So you'll definitely be able to read and follow that. So there you go. That's E for Barry and me. Woohoo! We wish you, a happy day, and I hope you're having a good time and enjoying the exponential growth and decay, if that's your jam, and that you know that you're totally awesome and amazing and brilliant, and that I hope you math on. Woohoo!